So thank you very much for joining into this session. And we are going to start the lightning talks. And the first talk will be by Zoltan Udvarnoki. These will all be very short talks, 4 minutes. We can have 1 or 2 questions.
I will just quickly share my screen. Can I start? Sorry, do you hear me? Can I start? Everything's okay. So, hello everyone. I am Zoltan, a physics PhD student from Budapest, working on quantum computer applications, mainly for the financial industry. So, the question we are trying to answer is, when will quantum computers be useful in finance? One of the exciting applications for us is the quantum Monte Carlo method. Our aim is to estimate how far we are today from using quantum computers for this method, and also quantify the requirements to achieve quantum advantage with this application. So just quickly, algorithms that use random sampling to estimate the expected value of a function of a random variable are called Monte Carlo simulations. These methods are universal and are used in many fields. The error or the standard deviation of the estimate decreases with 1 over square root of n in the classical case, but with the help of the quantum amplitude estimation algorithm, we get the 1 over n scaling on a quantum computer. So this promises a quadratic speedup. It is certainly not as good as the exponential speedup of some algorithm, but this is a much more versatile algorithm. So the option is probably the most well-known financial product where numerical pricing can and has to be used. What we did is that we took the simplest type of these options and tried to price it with the quantum Monte Carlo method. You can see the distribution and the function, this hockey stick on the figure. We use noisy simulations in IBM Qiskit SDK combined with analytical Cramer-Rao error bounds for the amplitude estimation. And so an analytical error can be calculated easily only for depolarizing noise model here. In this way, we get an error estimate for specific noise model settings. But if we change, for example, the ratio of the 1 and 2 qubit gate errors, obviously the estimation error will change significantly, as you can see here. We don't know the future, which one will be realized, so this is not very nice. To mitigate this dependence on the parameters, we thought that it was a good idea to utilize another metric, the quantum volume. The good thing about quantum volume is that it takes everything into account and tries to measure the overall performance of the quantum computer. And indeed, although not a one-to-one match, we can almost pair a quantum volume with an error. You can see on the right that various noise models don't make much difference if we move from the gate error space to the quantum volume axis. And to give you something useful at last, here the continuous line shows you the relative difference in error between the classical and quantum version of the Monte Carlo pricing. We can see that from about 2 to the 60 quantum volume, the quantum version is better in this ideal scenario with depolarizing noise on 7 qubits. Now IBM is at 2 to the 8 quantum volume, the red line here. So we are not there yet, but slowly getting closer. Of course, if the noise is more complicated than this, as it is most certainly really hardware, everything gets messier. We will get a bias in the estimate, and etc. We are still working in that direction. So thank you for your attention.
Thanks a lot. And I want to see whether there are some question. No, not more. So you are doing it as a collaboration. It's an academic and industry collaboration, right?
Yes.
Yes.
That's
So
true.
how do you find such a collaboration? Is it like, I mean, it's unusual, I guess, coming from university to enter into such a collaboration. What were the hard parts and what were the nice parts? What were the bad parts?
Yeah, so I'm working with Morgan Stanley, and I am very fortunate because there are many scientists working, and my supervisor there is also a physicist, and he also teaches at the university. Gabor Fat, he was working at the Morgan Stanley. Now he's at the university full time. So it's not very hard for me. So this is a very good situation for me, and it was easy to find this collaboration with Gabor Pseudo University. So this is a fortunate situation.
Thanks a lot, and thanks a lot for this nice talk. Uh,
Thank
I
you.
mean, we have to unfortunately move on because these are going to be very fast talks, lightning talks. And next speaker is Pavol Neilinger from the Comenius University. Pavol, please.
Yes. Mm. So, dear Chairman, thank you very much, and hello to everyone. I would like to use this nice opportunity to present our work on quantum corrections to conductivity of disordered thin films. And these disordered thin films are well known in the community of quantum technology. These films usually are niobium knitted, niobium titanium knitted, indium oxide, and they are utilized in, they have plenty applications, and just to name a few of them, they are used in nanowire-based single photon detectors, parametric amplifiers, or in superconducting qubits. And these films are usually characterized by the transport properties, namely the sheet resistance, which is the resistance of a perfect square sample. Also, optical measurements can be utilized, spectroscopic ellipsometry and transmission measurements. And if these spectra are correctly evaluated, then these can provide precious information on the electronic properties of these materials. Usually, when these samples are studied, the correlation between sheet resistance, thickness, and critical temperature is studied. When we lower the thickness of the samples, the critical temperature is suppressed, the disorder in the films are increased, but not just the superconducting properties are changed, but also the conductivity in the normal state. So lowering the thickness results in the degrees of the conductivity. And this is well known, and usually the conductivity, the optical conductivity, is considered as a regular part plus a perturbation, which are called quantum corrections, and they are negative. So the regular part is often taken as the 2D conductivity, and the quantum corrections, the function depends on the dimensionality of the system. Now, one can combine the transport and optical measurement by taking into account the excitation energy, omega, there is the frequency and the temperature, the physical temperature of the samples. This way, the transport and the optical measurements can be evaluated and plotted in one graph. And on this slide, I would like to present the conductivity, the optical conductivity obtained for a molybdenum carbide thin film, a 5 nanometer film with high level of disorder. What is interesting that we combined transport measurement, this is DC measurement, so we just measured the resistance of the sample, and optical transmission measurement and ellipsometry measurement. Here on the X scale, this is a root square dependence of the energy, and we see that this strongly deviates even in the optical range around 1-2 electron volts from the expected one from the Drude model, which is emphasized by this orange line. So our conductivity is very smooth and strongly suppressed. To analyze this, we introduced a model function which accounts for this square root dependence below a certain threshold frequency, and above this certain frequency, we just join the dependence of the conductivity to the expected to the conductivity. This way, we were able to fit to these conductivities and obtain the parameters of our samples. So this is an important result which shows that these quantum corrections, which are usually considered to be low energy or low frequency or low temperature phenomena, are present already to very high excitation energies, and thus the parameters which we usually take into account when considering the quality and the properties of our samples are already strongly affected by these effects. But as we see, now obtaining these parameters really depends on the function we are choosing, and for this reason it's quite desirable to have a method which allows the extrapolation of the conductivity, which is model independent. And we developed such a method, especially considering the properties of highly disordered thin films, namely that the spectra are smooth and not oscillating strongly. Here's an example of this extrapolation method for our film. Here's the conductivity, normalized conductivity for MOC film, the transmission and the spectroscopic ellipsometry measurement, and the method generates curves which fulfill the Kamas-Krennig relations, and at the end averages the resulted curves. This way we can obtain a final extrapolation which fits our experimental data very well in a broadened range. What is very interesting, that similarly for niobium knitted, we can obtain this extrapolation, and also niobium knitted with this material which is broadly used for superconducting technology. The expected spectra strongly deviates from the usually considered one. And this numerical extrapolation method can be of help in the understanding and testing of material, and present a robust local non-contact method for testing. So thank you for your attention.
Thanks a lot. We have to hurry. There were no questions, but can you go? I have one comment. Can you go to slide number 2? It was extreme that
Yes.
you had those transport ellipsometric and transmission measurements, and they on the different overlapping levels they coincided, right?
Yes.
That says something. You have
Yes.
different measurement and they coincide. That's great, actually.
Yes, exactly. That we have three independent measurements that really shows that these corrections are there and follow the square root function.
Yeah, thanks a lot. So we have to move on. Thank you very much.
Thank you very much.
Third speaker will be Peter Rakyta from Utrecht University, who will speak about using FPGA-based data flow engine to speed up the simulations of photonic quantum computers.
Okay, thank you, Zolvi. As you can see, I have now a better title of my presentation on the slide. And as Zoltan said, I tell you about our recent benchmark on how to speed up boson sampling using classical devices. The design of boson sampling is quite simple. Let's just take a photonic interferometer with some photonic modes, inject some input photons on the input modes and measure the output, and this way you can determine the probability distribution of the photon counts on the individual state configurations. And the work of Scott Aronson and Akripov already showed that the simulation of this system is classically intractable, because in the heart of this simulation lies the permanent function, which is very hard to evaluate classically. Even if you take the most efficient classical algorithm, it still scales exponentially with the size of the matrix. By the way, here in the bottom row, you can find the riser formula and the BBFG formula, which are currently the most efficient formulas to evaluate the permanence. So our aim was to come up with the most efficient implementation to calculate the permanent function to somehow speed up the boson sampling simulation. To this end, we managed to come up with an implementation using FPGA card. The FPGA is an acronym for Field Programmable Gate Array. Basically, on the FPGA chip, you have many small pieces of hardware element that you can program at the start of your numeric execution. And if you manage to tune the hardware elements properly and you stream the matrix through this chip, you can manage to get the permanent as the output. Okay, this sounds very easily, but we have a half a year to have it done. So there was much work, mostly done by our PhD student Gregory Morse. But the benchmark results of our implementation are very robust. Here is in the figure, we are comparing the execution time as a function of the matrix size. We compare our FPGA performance to state-of-the-art CPU implementation. For example, here the black line represents the implementation coming from the strawberry fields developed by Xanadu. The red line is the benchmark of some Chinese group, and the blue one is the CPU implementation coming from the Picasso quantum computer simulator, which is developed by our group. And also this newly developed FPGA-based data flow engine is fully connected to the Picasso framework. And as you can see, we can speed up the FPGA evaluation bar 2 orders. And if we apply if we split the computation between 2 FPGAs, we can further increase the computational speed. But that's not the whole story. The important thing is that we are doing this computation with high precision, with a precision equivalent to long double arithmetics, which is completely an advantage over GPU technology. You can do this on GPU. Okay, so this is one important message of our work. And finally, we could connect this permanent calculating engine to the boson sampling algorithm coming from the work Clifford and Clifford. And we compare our capabilities of boson sampling with real experiments from 2019, where they had 60 mode interferometer on an optical table and injected 20 photons into the interferometers and made some measurement. Our current limit is to do, okay, you don't see it. Our current limit is to do 40 photons to sample from 40 photons in a 60 mode interferometer and taking a single sample in something about 400 seconds. And of course, this is a result made on a single FPGA. If you have more FPGA, you can scale up your computations. Okay, so maybe this is not so good news for experimentalists, because you see there the experimentals are quite still far away from which can be simulated efficiently on classical hardware, but this result can open a door to study some quantum algorithm that is built on boson sampling simulation, on boson sampling, of course, and uses just classical hardware to do these studies. Okay, so this is my final message, this benchmark of 40 photons, and this is all from my side. Okay, I would thank for your attention, and maybe if you have a question, then I would like to answer it.
Thanks a lot. Sorry, I got cut off a little bit. Okay, there is one. We only have time for two very short questions. There is one question from Radu Marginean. How much can you scale up? I guess you already answered this question.
The boson sampling algorithm. Okay.
I guess he means
each FPGA can take one sample. If you have 1,000 of FPGAs, you can take 1,000 samples in this time.
Okay, so I have other question. And the other question is that I guess you put in a lot of energy and so on. So how would you see if somebody wanted to go and buy FPGAs and use data flow computing? Should they approach you, or they can build, or is it as easily built?
Well, we are strongly, not strongly, but closely collaborating with Maxeler Technologies. So they are providing the hardware and the development environment for this whole story, and we are giving the quantum computational ingredient to this story. So we are developing Picasso, and Maxeler has a 20-year-old experience in data flow technology.
Thanks a lot, Peter. So the next speaker is Adrian Ortega, and actually Orsoya Kalman already highlighted that you will talk about this benchmarking quantum computers using the quantum state matching of qubits, which is closely aligned with what she talked about. So Adrian, I cannot hear you. Do you guys hear me?
Yes, Zoltan, you are audible.
So what about if we would move on, and you can go on be the first in the next session? Could we do that, Adrian? And you fix your sound problem?
Probably now.
Okay,
yes, we can hear you.
Now.
Yes, now we can hear. Then please go ahead.
Okay, thank you very much. I'm sorry for this for this problem. So thank you, Zoltan, for the introduction. I work as a postdoc in the Wigner Institute, and this is a joint project done by with Orsoya Kalman and Tamas Kish. And Zoltan said this is like one of the projects that Orsoya described in the previous session, which is we still think that there is some room for making benchmark these new quantum computers. So essentially, we are going to use a quantum matching state protocol that uses a super attractive map. This is a reference where Orsi and Tamas developed the theoretical algorithm. So essentially, as we saw before, for one step of the protocol, you have the initial state, which is just a linear combination of 0 and 1, and then you can describe it essentially with this only one complex number. And then what you do is to prepare two qubits in the same quantum state, and then you would like to achieve this quadratic transformation. And now here, the interesting part is that you have some epsilon parameter, which essentially is a parameter in the complex plane that is going to tell you how many states inside this circle are going to be attracted either to the state 0 or to the state 1. So for instance, suppose that the state that I want to match is the state 0, then after a computation, I obtain some state that is perhaps close to this state. And then with this protocol, what it does is to, by applying it a certain number of times, this state is going to converge to the 0 state. If this state is outside the prescribed circle of radius epsilon, then this state is going to be, so to say, orthogonalized. So in order to achieve this, we need to implement this U epsilon matrix, which is the one here. And then essentially we have to decompose this matrix in basis gates such that the real quantum computers can understand it. So essentially this is our circuit that we implement in the real quantum computers. So we have just a state for state preparation. One part of the circuit is for state preparation, and the other is essentially the U epsilon. So you can see that if we apply several steps, it is essentially the same circuit, just applying to different combination of qubits. And this is in a nutshell the results that we have obtained so far. And here we have tested like a lot of quantum devices already. So essentially, if you notice in the previous slide, this complex number can be decomposed into two phases. And now, essentially, the results here I just organize it as a function of these two parameters. As a function of theta, you could, for instance, analyze what is the angle that you obtain after one step of the protocol. So this means that you start, for instance, inside the circles of radius epsilon, and after one step, you are going to get closer to the state 0. If not, you are going to stay farther away. And here we just test one of the IBM quantum computers for different values of this parameter epsilon. And here the first outcome is the results without error mitigation and with error mitigation. And then we have like a huge improvement. By the way, this is just the classical error mitigation where you do the tomography on the detectors and then apply just a linear transformation to adjust the results. Also, for one step, you can just also look as a function of phi. So this algorithm is such that if you select one angle theta, no matter what is the value of phi, theoretically you should obtain the same probability after the number of steps that you select. And in this case, what we have in this right part is the mapping for several thetas, and for all let's say all values of phi. What are the counts that we obtained? So, for instance, here in the right side, we can, in the right side, you can see the theoretical value, which is encoded here as colors, and then here the measurements for different angles. Then you can see these experimental variations. These are the two post-selected states that we need. And now, returning to the angle theta, you can also we try to find a quantity in which you can clearly distinguish the result, which is statistical, which is just only for the number of counts that you have, compared to the, so to say, the device error. And then this is what we do in these plots here. Essentially the success probability for one step of a protocol and for two steps as a function of the number of shots or a number of experiments in several quantum computers, including IonQ and Rigetti. And then similar to what we did in these color plots, we fixed the initial state, which in this case is still pi over 8, but we change here the values of phi.
Okay,
and then you can see
up, Adrian, I think soonish.
Yes, sure. Just I want to point out that you can see some interesting stuff. For instance, that you can see differences between the same quantum computer by just changing a few parameters of this protocol.
What do you add? Difference in which sense?
So difference in the sense, for instance, here we have 2 steps, but we select different qubits in the
between the qubits, you can see differences between the qubits.
But yeah, and also between the devices, because this,
okay,
for instance,
exactly. And then my question, nobody posted a question, so let me ask final question: which device turned out to be better, IonQ or Rigetti?
Well, this is almost a surprise because, for instance, these pink points are for IonQ. And if you look at it, I mean, Rigetti is always like worse than all the other examples, but the IonQ is closer to the IBM results that we obtained.
So the surprise is that that although it's better than Rigetti, you didn't get that it was better than IBM, right?
Exactly,
it's interesting. It's interesting. Yes. Thank you very much.
Okay.
And
thanks.
in this session, we are unfortunately behind time. There are two more speakers, and actually in these troubled times, it is with a special support we are introducing both of the speakers, because they are from Ukraine, and the first speaker will be of the two last is Oleg Turutanov from the Low Temperature Physics Institute in Kharkiv. Please, Oleg.
Just a moment. Do you see full screen or?
No, it's not full screen yet.
So, it's okay?
No, although I would, can you, so maybe you should set your full, the entire screen, not like an application, and then go on the full screen view.
Entire screen, okay. And the switch to application.
So the full, yeah, and then just not do. Now it's okay. Good. I think. Yes. Thank you very much, Oleg.
Well, hello. I represent one of the two Ukrainian groups involved in an international project, which is a collaboration of 5 teams. And I'd like to make a short overview of the subject to which the project is devoted to. There are too many participants in the project, so I was unable to enlist all of them. There are a few PhD students and researchers in each group. The microwave single photon detectors are still experimental, unlike optical ones, which are even commercially available now. The reason is the small photon energy, which, as you see, much smaller than the energy of the infrared photon. So this causes some issues. You see, it's a low operational temperature, and the problem of isolating qubit from external environment, and ensuring low back action of the measuring circuits. A flux qubit is just a superconducting loop interrupted by a Josephson junction. With proper parameters, it has true-well potential and a required energy level structure. It's controlled by 2 gates. Photon-induced transition and further relaxation to lower states cause a change in magnetic flux in the qubit loop, which is measured by radio frequency squid readout. Then the qubit is reset to its initial state to be ready to take the next photon. The red explosion signs indicate design features that help us in lowering back action and isolating qubit from the electromagnetic interferences. Sorry, you see the schematic diagram of the full SPD, and also our designs of 3-layer magnetic shield and low-pass metal powder filters, which are used in this scheme. So I'd like to emphasize some newly developed design features we use to make back action small. One of these an radio frequency squid in its non-hysteretic mode, but with non-linearity parameter detail close to unity. And the driving frequency elevated from common 30 MHz to 5000 MHz. This ensures high conversion rate ratio, but absence of dissipation. Also, the driving amplitude is very small, a few thousandths of flux quantum, and it means that has small influence on the qubit. Next, we use a cool down to 20 millikelvin amplifier on a HEMT in so-called unsaturated regime. This gives only 1 microwatt consumption and low brightness temperature of the two-dimensional gas in the channel. That also means no additional back action. All this is needed to avoid extra dark counts of the counter. This short report, I cannot cover all interesting aspects of the project, and it is still in progress, and we're all, in our collaboration, hope for successful experimental verification. So, thank you for your attention.
Thank you very much. There are no questions in the question and answer feed. Actually, there has been no question at all except one. So thank you very much. And what do you guess that how good qubits can you make with this method?
This is strictly saying this is not a qubit. This is a bad qubit. It
Sure.
It must have some dissipation, but very certain amount of. It's about 10 kilo ohms of overall loss, which could be ascribed to Jefferson junction.
Okay, thank you very much. So we go on to the next speaker. So originally, and also I think in the program, it was Elena Zhitlukhina from the Donetsk Institute for Physics and Engineering, but instead her co-author will talk, and the co-author is is Mikhail Belagorovsky from the Kiev Academic University. Thank you, Mikhail, and please.
Thank you very much for the introduction. Unfortunately, Elena, during these hard times, is in Poland as a refugee and has some problems with connection to the internet. So she asked me to present our joint work, and this work has been done together with Slovak colleagues. And so my talk is about superconductivity. It is well known that the superconductivity is a macroscopic quantum phenomenon arising due to coupling two electrons with opposite spins and opposite momenta into Cooper pairs. And the trivial phase diagram for simple superconductors looks as well here, but those which are used for different technological applications are not follow this scenario, but a more complicated one. So if we look at the phase diagram of the superconductor, known as type 2 superconductors, we can see not two but three different regions. First of all, it is the superconductivity. After that, if I increase the magnetic field, there is a mixed region where the magnetic field penetrates into a superconductor as vortices, which has a normal state core and circulating around them superconducting currents. So, due to this trick, a superconductor can survive till higher magnetic fields, and that is why such materials are used practically. Unfortunately, if I want to use them for transport purposes and connect them to a current source, in this case, there is a Lorentz force which moves the vortices, the dissipation appears, and therefore it's already not in a superconductor but a usual metal with a finite resistance. How it was solved before it, this problem? It was solved by immobilized the vortices. So, or by other word, to pin the vortices. So, very small nanoscale normal regions were introduced into superconductor up to some critical currents. The vortices were staying at their places, and the supercurrent could go across such assembly. What we proposed is to pin not the normal state cores of the vortices, but to pin the magnetic field penetrating into a superconductor. It can be done by placing a ferromagnetic layer, a thin ferromagnetic layer, is a very homogeneous magnetization texture near the superconductor. In this case, if you have some vortices here, they are stopped by interaction between magnetic fields penetrating into the ferromagnetic nearby layer. This, in our opinion, this way is better than the traditional one, since we do not touch the superconductor, do not suppress its superconducting properties, and all will be done by the nearby ferromagnetic field. The experiments were done in Bratislava, in the Comenius University, and by with for different combinations of superconductor and ferromagnet. As a superconductor was used niobium nitrogen with a critical temperature about 15 Ks, and as a big ferromagnetic layer, it was nickel copper, and so I show here only two combinations. So the trivial one, it's simply niobium nitrogen film, and more complicated where two films were divided with an insulating interlayer, so to prevent from the proximity effect. And here you can see that here is the resistance of the superconducting film. The critical temperature is the same for both configurations, while the critical current was increased more than 2 times by the presence of the nearby paramagnetic field. These are our first results, and we would be glad if we find partners who understand better in magnetic properties, in the properties of magnetic materials, yes, and have such hardware. So resuming, we have proposed a new way and realized a new way for pinning vortices and succeeded to increase more than 2 times the critical current, and we want to continue our joint activities. Thank you for the attention.
Thank you very much. And it was really a great talk about the Central and Eastern European collaboration between Slovakia and Slovakian Institute and Ukrainian institutes. So, do you have already plans of contacting people working in experimental magnetism or something like that? What you said were needed for the further work.
We have not concrete plans at the moment, but we would like to find them, and we would be happy to find them in the Eastern Europe.
Thank you very much. And this concludes this lightning talk session 1. And we immediately move, because we are short of time, to the next session, but we have to get, in this Airmeet platform out from this session and go to the next one. So thank you very much for all the talks.